Have you ever gazed up at the night sky and wondered why we haven't stumbled upon any extraterrestrial neighbors yet? Do you find yourself watching bizarre and highly speculative space docufictions discussing conspiracy theories of how aliens might have already visited us and how the government is trying to hide everything from us at 2 a.m. in the morning? Well, buckle up, because today we're diving deep into the cosmic conundrum of why aliens remain elusive. Watch till the end as we try to uncover the actual truth amidst all the cacophony of scientific speculations and paradoxes. Let's go. In April 1960, a Cornell University astronomer started a very interesting and unique experiment called Project Ozma at the National Radio Astronomy Observatory, Green Bank, West Virginia. The purpose of the experiment was to search for signs of extraterrestrial intelligent life through detection of interstellar radio signals. This was the first systematic experiment conducted in this field. A year later, in 1961, this radio astronomer formulated a simple equation to serve as a conversation starter for a first-of-its-kind conference on the topic of search for extraterrestrial intelligence. This simple equation would start a serious scientific discourse on the topic and would go on to become one of the most popular equations of our time. The astronomer in question is Frank Drake, and his equation is the famous Drake equation. It is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Here, R is the average rate of star formation in our galaxy per year. Fp is the fraction of stars that have planetary systems. Ne is the average number of planets that can potentially support life. Fl is the fraction of potentially habitable planets that actually develop life. Fi is the fraction of planets with life where intelligent life evolves. Fc is the fraction of planets with intelligent life capable of communicating with other civilizations. L represents the length of time for which civilizations release detectable signals into space. This factor accounts for the duration over which a civilization might be capable of communication before becoming undetectable due to factors such as self-destruction, technological obsolescence, or natural disasters. When we multiply all of these factors, we are supposed to get the total number of active, communicative extraterrestrial civilizations in our galaxy. Now, the interesting fact is that we can only correctly estimate, to some extent, the first three terms of the equation using our current knowledge and technology. The rest of the four terms are highly speculative in nature, and the quest to estimate them has given rise to numerous speculative theories, assumptions, and paradoxes. As such, the value of n varies greatly across various estimates, none of which can be confirmed to be right or wrong. As interesting and popular it is, the Drake equation does not actually provide a precise number of alien civilizations, but rather stimulates scientific dialogue and investigation into the factors influencing the existence of extraterrestrial life. Although there is no way for us to correctly estimate n using our current level of knowledge, we may be able to do so in the future in light of new information being available to us. But paradoxically, this equation itself can become a hindrance for us in our quest to expand our knowledge on extraterrestrial intelligent life. Let's see how. As far as the current state of scientific or intellectual discussion on the topic of extraterrestrial life is concerned, the majority of it involves an approach which could be restrictive and limiting in nature. Majority of the research revolves around an attempt to find life, which is more or less similar to life on Earth and on a planet more or less similar to Earth. Although there might be a few exceptions, that is what the norm is. To illustrate, let's consider the Drake equation and see how it becomes increasingly limiting. The first factor, which is the rate of star formation, inherently assumes that the possibility of life to emerge necessitates the presence of a star. But this does not need to be true. There can be celestial bodies harboring life in places we might not have expected. Like in a nebula, around a black hole, or in a rogue planet in interstellar space. Who knows? Consider the next 3 factors estimating the probability of an inhabitable planet that supports life. Like earlier, this does not necessarily have to be true. Life might develop in systems very different from traditional planets or even moons. It may be on an isolated rock traversing the galaxy, like in a comet. Or it may not even be entirely organic in nature, at least not in the sense we envision. The next factors revolve around the idea of evolution of intelligent life capable of communicating. And the assumptions for these can be highly limiting and biased in terms of our own understanding of what it means to be intelligent and what forms of communication could be there. Our own communication mediums have changed quite a bit in the last 50 years. Who knows what it would look like in 100 or 1,000 years? If we would have told someone from 1,000 years ago that we would be communicating with someone thousands of miles away through invisible waves, they would have considered us mad or a witch. So, trying to ascertain the communicating capability of an extraterrestrial intelligence with the understanding of our current communication technology is not only highly limiting, but futile. The same is the case with intelligence. Our definition of intelligence could be extremely narrow considering the fact that we are only looking at it through the lens of human intelligence. There can be some higher form of intelligence which our tiny brains may not even be capable of comprehending. Who knows? To arrive at a logical conclusion of our reasoning, we can safely say that we need to look at the universe through a rather open mind and not limit our thinking to confirmations set by our current level of knowledge. But adhering to a certain degree of confirmation may be necessary. Let's see why. During a casual lunchtime conversation in the summer of 1950, Enrico Fermi, the Nobel-winning physicist, remarked to his colleagues, "Where is everybody?" The crux of the discussion was that given that our solar system is quite young compared to the rest of the universe, roughly 4.5 billion years old compared to 13.8 billion, and that interstellar travel might be fairly easy to achieve given enough time, Earth should have been visited by aliens already. This gives rise to the Fermi paradox, which is the discrepancy between the lack of conclusive evidence of advanced extraterrestrial life and the apparently high likelihood of its existence. This is where the need for constraints in our assumptions while calculating the probability of finding extraterrestrial life arises. Consider the 2 extreme possibilities. In one extremity, there are no constraints on our assumptions, and life can be of any form and appear anywhere, giving rise to infinite possibilities of extraterrestrial life. In the other extremity, there are multitudes of constraints which results in the possibility of life appearing only under certain strict conditions, similar to conditions on Earth. This is also known as the rare Earth hypothesis, which says complex extraterrestrial life is an improbable phenomenon and likely to be rare throughout the universe as a whole. Life on Earth might be the only lucky accident. The Drake equation lies somewhere in the middle of the 2 extremities, with its reasonable assumptions. When we compare this side by side with the Fermi paradox, we see that as we move towards the infinite possibility extreme, the paradox becomes stronger, which basically means the observable universe should have been teeming with life, and we should have found at least some proof of it no matter what. But when we move towards the rare Earth extreme, the paradox disappears, and it aligns with what we observe empirically too. No proof of life because there is no life. This, however, is a scary possibility, perhaps scarier than the opposite one, which gives rise to the possibility of the existence of a dangerous alien race with the capability to annihilate us. But where does the actual truth lie in all of this? In human scale, our universe is unfathomably large and extremely ancient at 13.8 billion years old. To put that in perspective, if the universe were a year old, our modern industrial civilization would have existed for mere microseconds now. Our observable universe is estimated to be about 93 billion light-years in diameter. If we consider ourselves to be at the middle of the observable universe and we send a message saying hi to either end, it would take 46.5 billion years for the message to reach there, by which time we might be long gone. To put that in perspective, it has been a mere 4.5 billion years since Earth came into being, and 3.7 billion years since the first life appeared on Earth. Even if we were to travel at the speed of light from Earth the moment the first Homo sapien ancestors emerged, we would not have covered even 0.00001% of the observable universe. To bring it home, here is the Milky Way galaxy, about 180,000 light-years across, and this tiny blue dot 200 light-years across is the extent of our radio broadcasts. So, to say that extraterrestrial life may not exist because we haven't found any signs of it yet would not only be immature, but outright hubris. As famously put by Neil deGrasse Tyson, claiming there is no other life in the universe is like scooping up some water, looking at the cup and claiming there are no whales in the ocean. Maybe we haven't been here long enough and haven't reached out far enough. Maybe our technology is not mature enough. Maybe we aren't significant enough yet for advanced civilizations to contact us or care about us. And maybe someday, we will get there, and we will make first contact. Until then, it is okay to speculate and wonder about the possibilities and impossibilities. Thank you.